G'day viewers, just explaining the trip to Mars estimation that I made some time back. It was just a guess, well, an educated guess. You know, you can rapidly approximate nearly anything. So we actually did the calculations, and I'll explain my calculations here. Mars has a minimum distance of 54.6 million kilometres and a maximum distance of 401 million kilometres from Earth. Earth being our starting reference point. Now I said a day accelerating and a day decelerating at 1G. That would give the crew a Earth feel, and you know, it's more healthy for a human to be in a gravitational environment. This has been proven by many thousands of hours being spent in space by astronauts and cosmonauts. A lot of study has been gone into the gravitational effects or microgravity effects on the human body, and it's my proposition that we use gravity to our advantage in space by generating gravity through use of Einstein's equivalence principle. We know that gravity and acceleration have the same effect. You cannot distinguish between the two. So on saying that, if we accelerate at 1G, which is 9.8 metres a second squared, for 24 hours, the distance S is equal to 1/2 times AT squared. Now, if you punch these numbers here into this calculation, you'll find out you'll do about 36.6 billion metres, which rounds down to 36,615,600 kilometres. Now that's only significant to 6 digits. There are actually smaller numbers that go in here. I think it's 28 or something. But that's close enough. That's within a percent of the answer. So the distance travelled after 24 hours is 36.6 million kilometres, and that's 24 hours of deceleration will give you the same distance. So you add these two distances up and you end up with 2 days of travel time under 1G at experiencing 1G of gravity, or the same as 1G of gravity, a very Earth-like feeling in space, you might say. You'd end up travelling 73,231,200 kilometres. Now these are just done on phone calculators and online calculators. I did it. I actually got two different outcomes, but they were so close you could say these are all good enough. Here we got 2 days cruising at 3 million kilometres an hour. Now you might think 3 million kilometres an hour is a lot. It's not even anywhere near 1% of light speed. So this is a non-relativistic speed. It's below 1%. I think it was about 0.22 or somewhere. Anyway, it's not that. It doesn't affect the calculation. It's very slow compared to how fast some things move in the universe. So here we've got 2 days cruising, and we end up with 146,462,496 kilometres of travel. That's 2 days cruising weightless. Now this is not my end proposition. I'm actually propositioning of the trip to Mars under 1G of effective gravity at all times. So when you arrive at Mars, your body's physiology is not affected. But in this trip where we're experiencing gravity, and then we've got 2 days of weightlessness or microgravity, you will cover a total distance on the 4-day trip of 219,693,696 kilometres, which is above the average distance from Mars. Now obviously you don't take off for Mars any old time. You've got to look for the right launch window, you've got to calculate the distance. There's lots of factors to take into consideration, but for a simple explanation, there's your 4-day trip to Mars, there's your total distance you can travel, and in fact Mars is, I think it's about 150 million kilometres away at the moment, so you could probably do it, looking at those figures, in a little bit over 3 days. So that's my answer for the 4-day trip to Mars, and at the minimum distance you could actually do it in under 2 days quite easily. So stop putting this barrier up there that Mars is too far away and it's too hard, no, we can't get there, and there's a better solution, and here's the mathematical proof. Thanks for watching, and here's something for you to think about, and you got a few more videos coming on this whole subject, and anti-gravity and antimatter. Anyway, we'll talk later. Cheers.